Hello everyone, and welcome to the period of a mass on a spring post-lab. Now this lab had a couple of parts to it. In the first part of the lab, we were looking for the relationship between the period in seconds and the spring constant in newtons per meter. This one took a little bit to linearize. When you started out, your graph looked like this, which is basically a hyperbola. Now, it may not have been as noticeable of a hyperbola as this. It probably was a little bit straighter, right? But that's because we didn't have a huge range of spring constants to use, just the ones that we had available in the lab, right? So we kind of had a smaller piece of this curve, which does somewhat look like a straight line, right? So our first attempt to linearize a hyperbola is usually to invert. So you graphed period in seconds versus 1 over the spring constant, and notice you flip the units in meters per newton, and that gave you a side opening parabola. Again, probably pretty weak, right? But still a side opening parabola. Well, how do you linearize that? Well, think about what we've seen many times this year, which is a top opening parabola, right? A top opening parabola you square. Top opening parabolas get steeper and steeper. Well, this is kind of the other function, right? It's getting less and less steep, so maybe you square root, right? So if we do period versus 1 over the square root of the spring constant, this is technically the square root of this whole thing, but the square root of 1 is 1, right? In units of square rooted meters per newton, right? Then you got a very straight line. And I don't know if you checked, but if you actually did a linear fit on the last two graphs, this graph would have a better correlation, closer to 1, than this graph would, showing that this is a better representation of the relationship between period and spring constant. So since this third graph gave you a linear graph that went through 0, 0, we can say that the period is inversely proportional to the square root of the spring constant. Whew! A couple ways. Period is proportional to 1 over the square root of the spring constant, or using the magic word, period is inversely proportional to the square root of the spring constant. Fairly complex relationship there. If we build a math model out of this third linearized graph, we get the y variable is the period, because that's what we graphed on the y-axis. That equals your slope. For reasons which we will see in a little bit, I'm going to say your theoretical slope should be around 4.69. Right, which I think is about what your slope was, right? If you put it in the computer and it took it, your slope was certainly within about 5% of this. So let's check out the units. The units of this would be units of rise, seconds, over units of run, square-rooted meters per newton. That doesn't look like something we can simplify, but remember that a newton is a derived unit. It is a kilogram meter per second squared. So the meters cancel. The second squared gets flipped up to the top of this fraction, and then square rooted. The second square rooted would be seconds, so they cancel. Right. And then we are left with then 1 over the square root of 1 over a kilogram, which would flip to make square root of a kilogram. A lot of algebra there. But in the end, it ends up being square root of mass units. Now, this is not the square root of the mass, right? Not anywhere close to the square root of your mass, but it must be related in some way, and we'll see that pop up as we continue with the post-lab. The x variable is, of course, 1 over the square root of the spring constant, and the y-intercept here is 0. Although, because this is an inverse relationship, that really means that as the spring constant approaches infinity, the period approaches 0. Right? If we look at the original graph, the bigger the spring constant gets, the smaller the period gets, right? Because if the spring is stronger, it's going to vibrate faster. Right? So it kind of makes sense that bigger spring constants have smaller periods. And in this part of the lab, we used a constant mass of roughly this. Yours might be a little bit different depending on your piece of cardboard and that kind of thing, which may have a slight effect on your slope. But notice, the square root of this is not 4.69. So there's got to be something going on besides the square root of the mass here. So this is the first half of the lab. Second half of the lab was period as a function of mass with constant spring constant. Right? So we used one spring and varied the masses. And when you graphed that, you got a side-opening parabola. Well, we just saw how to linearize a side-opening parabola. You take the square root of the x value. So here we graphed period in seconds versus square root of the mass in square-rooted kilograms, and that gave you a linear graph that went through 0, 0. Hence, the period is proportional to the square root of the mass. If the mass quadrupled, the period would only go up by 2. If the mass went up by 9, the period would only go up by 3. Right? Notice that means the mass increases faster than the period does, which is why the graph gets less and less steep. We make a math model out of our linearized graph. The y variable is, of course, the period. And that equals the slope, which I am going to say should be around 0.993, give or take a little bit, which, again, should be pretty much right around your slope. Units are a little simpler in this case in some ways. At least we don't have to simplify them. Rise, units of seconds. Run, units of square-rooted kilograms. Not some combination we've seen before, but no way to really reduce those. We'll see how those pop out here as we go. The x variable in this case is square-rooted meters, and the y-intercept is 0, because if you have no mass, you can't have a period because it won't stretch the spring, and therefore the spring won't be able to oscillate. In this half of the lab where you varied the mass, you kept the spring constant at around 40 newtons per meter. All right, your slightly different spring constant might be why your slope is a little bit different than mine. Okay, that's one of the little sources of error, I suppose, for what I'm writing in here. But again, we'll see that as we continue. So, we now know two things. We know that the period is proportional to 1 over the square root of the spring constant, and the period is proportional to the square root of the mass. Put those two together, right? And the period is proportional to the square root of the mass over the square root of the spring constant. You multiply those together. Remember how we've done that before in multivariable labs? Right? You multiply them. And then we can redo this to make it look a little nicer. The square root of the mass over the square root of the spring constant is the same thing as the square root of the mass over the spring constant. All right, you okay with that little bit of algebra there? Okay, so here is our net relationship between the three variables, but it's only a proportionality. Yeah, it would allow us to say if we do this to the mass and this to the spring constant, this is what would happen to the period. Okay, but it doesn't allow us to calculate a period. For that, we need an equation. And to turn a proportionality into an equation, we need to throw in a constant of proportionality, which for now I'm going to call z, but you can call anything you want. Right? It's just a dummy variable for now till we figure out what it is. This is some number. Well, what number should that be? We are going to derive an expression for the period and compare that to what we just got in the lab. Okay? So we're going to derive the theoretical period of a mass on the end of a spring. So here's the vibration, right? Now I'm going to use a horizontal mass on the end of a spring because it makes the force analysis simpler, because then gravity doesn't really factor in, right? It's just due to the force exerted by the spring. That's why it's oscillating. So it's a little simpler to look at this and do the derivation this way. Yes, we could do it with a vertical spring. It'd just be harder, right? So let's analyze it when the spring is at positive maximum right there. Okay, let's draw a force diagram when the spring is here. What forces act? Well, of course, gravity and the normal force. But the spring is not accelerating up and down, and therefore they have to balance out. And if we're at this end, the spring is pulling back to the left, right? And that's the force exerted by a spring. Now, we have to assume this is frictionless, right? And it's an ideal spring situation, so we have no damping. So that we can, work this through and have nice, simple harmonic motion. So, the force exerted by the spring is, of course, negative kx, because that's Hooke's law, right? And we're using an ideal Hookean spring here. This is what we know, or what we call, a linear simple harmonic oscillator. Why linear? Because the force is a linear function of position. We can get more complex functions of positions and get different kinds of oscillators. We are going to stick in this class with linear simple harmonic oscillators, all right, which are a little bit easier to handle mathematically. So, force analysis, right? Net force horizontally is the mass times the acceleration, but the net force is just the force exerted by the spring. But of course, the force exerted by the spring, as we just mentioned, from Hooke's law is negative kx. Right? So we can plug that in here. Now, the acceleration is the acceleration of a simple harmonic oscillator, because we know that's what happens with the mass on a spring. And we have already, both experimentally and theoretically, derived an expression for the acceleration of a simple harmonic oscillator, which is negative omega squared x. Now be careful here. X in both of these equations is pretty loaded. All right, x is actually x sub m cosine of omega t plus phi, right? Because these are oscillating. So these x's are functions of position. Okay? So the force exerted by a spring, substitute here. The acceleration, substitute there. Omega, remember, is the angular frequency, right? And then notice what we get. We get negative kx equals m times negative omega square x. And what do you notice? The x's cancel. Now remember, again, that's this whole thing here, x of m cosine of omega t plus phi. That whole thing cancels, right? That includes, if you notice, the amplitude. Right? So here's in the math where it's showing us that the amplitude does not affect the period of a mass on the end of a spring. Right? Remember how we saw that experimentally. We saw that good video, right, of it. So why? Well, more amplitude means bigger forces, right? But it also means, more amplitude means bigger forces, but it also means more distance to cover, right? It would swing bigger distances back and forth, right? But the bigger forces result in bigger accelerations, which will allow it to cover that distance in the same amount of time. And because they both happen to be directly proportional to it, it cancels out. Okay, hard to see why that is without doing the math, and the math kind of leads us there. So that means we're left with, and the negatives cancel, the spring constant is m times the angular frequency squared. Which means the angular frequency, right, of a mass on the end of a spring is the square root of k over m. That's a handy thing to just know. Okay? This is only for the mass on the end of a spring. And by the way, this works the same if it's a horizontal mass on the end of a spring or a vertical mass on the end of the spring. All right? Because all that gravity stuff would just cancel out anyway. So, same equation. Okay? But that's not what we were trying to derive. We weren't trying to derive an equation for the angular frequency. We were trying to derive an expression for the period. But remember, we can write the angular frequency in terms of the period, right? It is 2 pi over the period. This is the, for the entire oscillation, right? For one entire oscillation, it will oscillate through 2 pi radians in a time of 1 period. Plug that in. We get 2 pi over the period equals the square root of k over m. Solve for the period, and there's our equation for the period of a mass on the end of a spring. At least theoretically, it appears that the period should be equal to 2 pi times the square root of m over k, mass over spring constant. So here's what theoretically the period is. And by the way, you're supposed to be able to do this derivation on a test if asked. Maybe it's part A of a free response problem, and they would ask you to prove that the period of a mass on the end of a spring is this. I believe this equation's actually on your equation sheet, right? But they could theoretically ask you to derive it. So, first half of the lab, this is what we got. Right? Theoretical is this. Well, let's rewrite our theoretical to look more like our experimental. See what I did there, right? I just moved the square root of m with the 2 pi and grouped it that way. Now, compare those equations. If our theoretical equation is supposed to be able to predict what we actually got in the lab, then the slope we got in the lab had better be 2 pi times the square root of the mass. With me there? That's the y, that's the x, y-intercepts of 0. So this has got to be the slope. Right? So, what is 2 pi times the square root of the mass? Well, in this half of the lab, we kept the mass constant. And you have your constant mass, so feel free to plug yours in at this point to work out what your slope should be. So mine, I said, was around 557 grams, or 0.557 kilograms. And if I take 2 pi times the square root of that, note I'm going to get units of square root of kilograms, just like I did here. And as a number, I get 4.69. This is actually where I calculated the slope. Okay, I measured one of the mass hanger cardboards, all right, that one of you was using, and said, okay, that's kind of what the average is for everybody, and, you know, calculated it using the theoretical equation. And certainly it seems to match. Well, let's look at your data results and see if that matches as well. So I've done something kind of fancy here with the Google form. Okay, here we go. So here are some constant masses, and you'll notice they average out to what, you know, I used in my theoretical, right? And then here's everybody's slopes. You'll notice that the slopes are fairly close to one another. We got a little bit of an outlier here, but still, right? All the slopes are in the same kind of ballpark. Okay, so we average slope for the class of about 4.85. But over here, look what I calculated. I calculated the theoretical slope from our derivation. I took 2 times pi times the square root of this mass. See, if I click on one of those, see the equation? 2 times pi times the square root of the mass. Okay? And then I did a percent error between the theoretical and the experimental and listed it right here. Okay? And we are pretty close. Okay, theoretically, our slope should be on average about 4.69, like I said earlier, using the 0.557 and calculating it. Right? Our actual slope in lab is about 4.85, which is pretty darn close, right? 3.5%. It's not as small as some labs we've done, but it's certainly a small percent error. I think most of the error probably comes in with the fact that our mass on the end of a spring, it's not an ideal spring, which we are assuming, right? And so that might affect kind of the results that we get. And I think that's probably the biggest source of error. Might be a little bit in the measuring of the period, although I think that the measuring of the period is probably fairly accurate as we measured 10 and divided by 10, that kind of thing. But so it's probably mostly the decay in the amplitude, right? Because it's not an ideal spring, all right? But still, pretty close, right? Only 3.5%. Now, just to confirm, let's look at the second half of the lab. There's our equation we got. There's our theoretical. So let's do the same process again and see if it matches. Here's the theoretical written to match the experimental. And again, for this theoretical to predict this experimental, right, the slope that we got in the lab had better be 2 pi over the square root of the spring constant. Right, so this had better be the slope of the graph that we got. Well, let's check it out, right? Because in this half of the lab, where you varied the mass, we kept the spring constant, and I assumed we used one that theoretically at least was supposed to be about 40 newtons per meter, according to the company. So if I plug that in, right, first off, let's check out the rather tricky units. Right, we get units of 1 over, technically it's radians, but those go away, square root of newtons per meter. Doesn't look like our units of our slope, but remember, a newton is a kilogram meter per second squared. So the meters cancel. A square root of a second squared is a second, and it flips up to the top, so we do get units of seconds per square rooted kilogram, just like we did in the experimental part of the lab. And 2 pi over the square root of 40 is 0.993. That's where I got this number. Let's see if your lab results match. And again, I did the same kind of fancy thing to this Google form. So here are some spring constants, right? Notice everybody's is pretty close to 40, give or take a little bit. Here is everyone's slopes. Again, pretty close to one another, right? Average it out to just a little bit above 1. Here are the theoretical slopes, taking 2 pi over the square root of the spring constant. And again, you can kind of see that here, right? 2 times pi divided by the square root of the spring constant column, right? And then here are the percent errors. And although we had one little outlier here, we ended up with about a 3% error overall. So again, pretty darn close, right, to matching here. Should convince you that the derivation and the experiment are both predicting reality. Again, I would guess that most of the error comes from the fact that the spring is not perfectly ideal. It's pretty close though, right? So only 3% error there too. About the same as the first part of the lab, right? So it seems that in fact, we can say that the period of a mass on a spring is 2 pi times the square root of m over k. I don't know why that left that at an angle, but you get the idea, right? That's our equation. Now, I want you to notice here this form, because we're going to see this form again for other simple harmonic oscillators, okay? Notice that the period has an element of inertia, the mass, and an element of springiness, right? In this case, the spring constant. It's pretty easy to track those in this case, okay? And this 2 pi factors in as well, right? So note this form, which we're going to see again, or similar looks when we look at other simple harmonic oscillators when we stop using just masses on springs, okay?